in this question, what we've been asked to do is to figure out the empirical formula of a given hydrocarbon. Now in this particular case, the hydrocarbon was burning excess oxygen, and we've been provided the mass of both carbon dioxide and water that was produced. Now, how would we approach this? Well, what we need to be able to do is compare the moles produced of the carbon dioxide and the hydrogen, because given it's a hydrocarbon, we know that the carbon and hydrogen produced came from the hydrocarbon itself, right? Now, the empirical formula, as we know, is the simplest whole number ratio between the elements present. So I've got this written out here, right? So, and what we're going to do is we'll start off comparing it like this. So what we do is we'll set it up like this. So if you refer to the periodic table, you would be able to work out the molar masses of both carbon dioxide and water. If you do that, you'll find that the MR, so I'll represent this as MR, so molar mass of CO₂ is equal to 44, right? And if you do this for H₂O, you'll find that the MR, so the molar mass of H₂O, is equal to 18, right? And we know from the equation that relates moles, mass, and molar mass that the mass, and I could just represent this as M, is equal to the well, actually what I'll do is I'll represent it, because what we're looking for is moles. I could do it this way, but you know, the mass is the moles times the molar mass, but we're really looking for the moles, so I'll put the moles on one side, right? The moles, N, is equal to the mass, M, divided by the molar mass, right? So MR. So in this format, we can figure out that, okay, what we need to do to get the moles of both the CO₂ and the moles of the H₂O is divide the masses given in the question by the molar masses. So in the case of the moles of CO₂, that's going to be equal to 118.976 divided by the molar mass, which we've worked out is 44, right? And on the H₂O side of things, so for the number of moles of H₂O, that's going to be equal to the mass of the H₂O, which is 24 point, let me just get rid of that just for clarity. Yeah, okay, 24.336, right? And well, that would need to be divided by the molar mass of H₂O, which, as we've figured out, is 18, right? Okay, so I would invite you to have a go at working out what each of these are on your calculator. If you had a go at that, what you should have come up with is that for the number of moles of CO₂, when you do that calculation, what you get is 2.704, right? 2.704. And when you do that for the H₂O, what you should get is 1.352. And what we can do now in order to try and get closer to that, establishing what is that ratio between the two, what we can do is effectively just represent this side by side. So the moles of CO2 compared to, as a ratio, compared to the moles of H₂O, okay? And that, as we've seen here, is going to be 2.704 compared to 1.352. And our aim is to get this to a whole number ratio, which it currently isn't. The first step, how I'm going to approach this, is I'm going to divide both sides by, in this case, the smallest number being 1.352. When I do that, that side of the equation is going to become a whole number, right? Because I'm dividing 1.352 by itself effectively, and that's going to give us 1, right? So I'm going to divide this by 1.352. And given it's a ratio, we do the same to the other side, right? So divide that by 1.352. And again, I would invite you to work out what that is on both sides on your calculator. Okay, so if you've had a go at that, what you'd find is that is going to be that's going to be equal to, wait 1 second, let's get rid of this. If you've had a go at that, what you should find is that this is going to be equal to, on this side it's going to be 2, right? So divided by that is 2. And on this side, as we already discussed, that is actually going to be 1. Now, the question we ask ourselves now is this a whole number ratio? Well, yes. At this stage, we already have a whole number ratio. But now we have to ask ourselves, well, what bearing does this have? What's the implication for this as far as the empirical formula? We need to remind ourselves that this ratio is not the ratio between carbon and hydrogen. This ratio is specifically the ratio between carbon dioxide and H₂O, right? So when we look now at trying to work out, well, given this, what is the ratio between carbon and hydrogen, right? What we have to look at is, in the case of H₂O, what is the ratio between carbon and CO₂, right? So for every carbon, we've got one CO₂, right? So we know that that's a 1-to-1 ratio. But when we look over here at the H₂O and we look at the ratio between hydrogen and H₂O, right? We know that for every 1 hydrogen, there is 0.5 H₂O, right? So we need 2 of these to get 1 of these. And therefore, we know that in the case of what we've got here, where we've got one H₂O and we've got 2 carbons, right? We effectively know that for each of the H₂Os that we find, there must have been 2 hydrogens. So we know that the ratio, if we want to make this like, okay, put it in a different way, for every, if we multiply this, for example, so we can do it here as well. If we multiply this to get a whole number ratio, we get that for every 2 hydrogens. So what I've done is multiply both sides by 2. For every 2 hydrogens, there's 1 H₂O. And given what we have here is 1 H₂O, we can see much more clearly that this means there's going to be 2 hydrogens, right? So what does that mean in the case of the carbon to hydrogen ratio? Well, it means that here we're going to have a 2, and on the hydrogen side, we're also going to have a 2, right? So that's a 2-to-2 ratio. Now, would this be our empirical formula? Well, we have to refer back to the definition of empirical formula, in that it is the simplest whole number ratio of atoms. This is not the simplest ratio because 2 is divisible by 2, right? And this would give us a smaller number if we do that operation. So this is exactly what we're going to do here. We're going to divide both sides by 2 to get this simplest ratio And so that is going to give us 1 and 1, right? Is this now our simplest whole number ratio? The answer is yes. This is now our simplest whole number ratio, and therefore, based on that, you know that. And I'm gonna actually add coefficients in here, just to show where clearly the corresponding numbers. But in the final answer, I'm gonna remove it, right? But this is effectively C1 H1, right? But obviously, when we have a 1 in our formula, we don't actually write it, right? So in our specific case, we would actually literally just write CH as the correct kind of representation. And so CH, in this case, CH is actually our empirical formula for this particular question. Okay?